nobody can watch it unless I give them a link. But it is recording, so I can give you a link later on. All right, here's what we're going to be doing. If you flip to the next page and you look at this map, it's really hard to see on the board, but there's North America, South America, all the different continents, and I've labeled a few different kinds of features. All these lines, they're a bunch of lines. Those are all plate boundaries. Those are places where one plate's hitting another plate. And you can see ones like this where the arrows are going apart. What kind of plate boundary is that? Come on, you know this. Divergent. And then there's one like the San Andreas Fault. What kind is that? And it says transform boundary. And then this would be a convergent. This is a convergent. So there are different kinds of convergent and divergent boundaries. And this one over here isn't even a plate boundary. It's a hot spot. Some of these happen in the ocean, and some of them happen on land. So that makes all of them a little bit different. And these pictures here, the goal is for you to be able to draw something like this and label all the stuff without me. So I've given you pretty detailed drawings, but we're going to practice doing these drawings. And my hope is that you won't be memorizing this stuff, that as we do it, it'll make sense, so that when you have a test over it, you don't have to memorize a bunch of things. It just makes sense. So you can just answer the test questions. All right. In order to do some of it, in order to figure out what's happening, we have to talk about two different kinds of rocks. There's mafic and there's felsic. And I'll remind you of all this stuff today. So this is dark. It says dark in color. That's this stuff. And it's more dense. So if you threw both of these into a pond, the dark one, the mafic one, would sink really fast, and the felsic one, it'd probably sink too, but not as well as the mafic one. Low viscosity, runny when melted. So this is the kind that's watery. Seems kind of backwards that the darker one is watery when you melt it. But if you melt this kind of crust, it's really watery. And because of that, it doesn't build up much pressure. And also, if you try to make a pile of water, here, you pour a bunch of water right onto this surface. Can you build a big, steep pile? No. The water just spreads out. So this kind of stuff doesn't build up tall volcanoes because it's not gooey enough. It's too watery. Has anybody ever seen a cow pie? Really? Okay. So anyway, cow poop is usually pretty watery. It spreads out into like this. You know, dog poop can pile up because it's got a lot higher viscosity. It's a lot gooier. Cow poop is always really runny, flattens out. But clearly you haven't spent a lot of time around cows, or some of you. So example, we'll come back to that. We don't need to talk about basalt. Of these two, this one is more dense. So if I took the Earth's mantle and I put some mafic crust on the mantle, and I put some felsic crust on the mantle, and this one is more dense, and this one is less dense, what are they going to do differently? And here's the mantle. The mantle is this hot flowing rock. I place these other ones on top of it. It's kind of like setting some stuff on top of water. How's the less dense stuff going to behave differently than the more dense stuff? Yeah, one's going to sink and lower. So what happens is this, if I draw a picture of how it would really look, here's the mantle, and this is this mafic stuff, and this is the felsic stuff. It's kind of like that. This floats up a little better, this sinks down a little bit, and if you pour water all over the Earth, where's it going to go? On top of the light stuff or on top of the dark stuff? Dark stuff. So this is found in ocean crust, and the reason it's found in ocean crust is because this crust sinks down lower, it sits lower, and water goes to the low spot on the Earth's surface. So all the dark kind of crust, that's that's in the bottom of the ocean, and then the light kind of crust, that's on continents. So let's see. It's called mafic. You don't really need to know, but you might be curious. It's a weird name. It's got magnesium in it, which is a metal, and it's got iron in it, which is a metal. And because of those two metals, it's pretty heavy. So that's why it's so dense. That's why it has a big density. And then this other kind of rock, again, you don't have to memorize this. I'll remind you. This is called felsic, and it's less dense. It's lighter in color. If you melt this, this has feldspar and silica in it. Has anybody ever found, gotten anything that needed to be kept dry and there are little packets in it that say silica packets, do not eat? So the silica, if you open it up, is kind of a clear looking thing. Silica is what you find in sand a lot of times, and it's in glass. So if you heat up silica to make glass, has anybody ever seen somebody blow glass? Is it runny or sticky? It's really sticky. I'll see if I can find a picture of somebody blowing glass. It's sticky and hot and dangerous, but it's definitely sticky. Blowing. And it's called blowing glass because you can actually just blow it up like this. There's this tube. Here's some really hot silica and other stuff that's in glass, and this person's just blowing air in there. And if this were runny, it would all just drip down on the table, but it's sticky enough that it goes together. So that's blowing glass. And here's pouring molten iron. So the glass, that's like felsic rock when you melt it. And this is like mafic rock. You can't blow this. It wouldn't form a bubble. It would just drip down. So, all right. So this is the gooey stuff when you melt it. This is the runny stuff when you melt it. This will pile up steep. This won't. Which one explodes more, the runny stuff or the gooey stuff? This is back to the warm-up. If I boil a pot of gooey material and I boil a pot of watery material, which one's going to start splattering? The gooey stuff, like the tomato sauce in the video I showed you. What else do we need to know? I guess that's it. All right, now we're ready to begin. And I could let you pick a feature to begin with, but I want to pick a feature to begin with. So here's what I'm going to do. We're going to go through. We've got 1, 2, 3, 4, 5, 6, 7 different kinds of situations to draw. And I'll pick the first one, and then you can decide which one we're going to do next. So if you look on your paper, here's the plate boundary. This over here, is this dark or light? You can't see it on my screen, but you can see it on your paper. Is this dark or light crust? The whole map is either dark or light. What part of the map is light? The land, the continents. So is this light? No. So that's ocean crust. And how about this plate over here? Is that light? Yes or no? Nope. That's ocean crust too. So go forward until we get to the first page that's blank looking. It's got some little check boxes at the bottom that we'll use. And we'll do the name. So the feature name, this is going to be an ocean, and that's just the names of the two kinds of crust plates. This is ocean crust and this is ocean crust. And what are they doing? Are they converging or diverging? Ones that I showed you on the diagram were doing this. Is this convergent or divergent? Hello? Chase, convergent or divergent? Thanks. All right, divergent. And an example is the Mid-Atlantic Ridge. Adding in a bunch of stuff here. Like I was saying earlier, my goal is eventually you could just draw all this yourself. And it's not really from memory. It's just because it makes sense. And so the first question is, how many plates do I draw? Anyone? It would be helpful if you would blurt it out so I get an idea if you know what I'm talking about. If you're silent, I don't know if you just don't want to say anything. How many plates? Just two here. Just an ocean plate and another ocean plate. So I'm going to draw it like this. Here's my ocean plate, and here's another one, and I'm leaving it blank in the middle for now because I want to have you try to figure out what's happening there. Okay, so stay on this page. I'm just going back to the other. Oh, I should rip this one out. I'm going to rip this out of my handout so I can show you this. These ocean plates, should they be dark or should they be light? Dark. Ocean plates are made out of mafic stuff. So this is the way I darken it so it's not too dark. I just kind of do some light lines like this, and we can add more in. So the ocean plates are the dark stuff, and you can do this in any order. Which way does this plate move? I want to draw the movements of the plates. Which way does this one go? It's got to go to the right because they're divergent. So this one goes to the right and this one goes to the left. Now, another thing you're going to have to draw is the thing that makes them move. What makes them move? Yeah, the mantle. So the mantle's down here. Now, is the mantle, think about this. This should make sense to everybody. Don't draw this. I'm just going to draw some clouds up here and maybe some birds and then the sun off in the distance. This is totally irrelevant, but I'm just trying to make it look like this is the surface of the Earth. So the next question, don't answer it yet, is the mantle going to be more dense or less dense than the crust? That's okay. I'd rather you answer ahead of time than not. So as you go deeper, things get more dense. So what do you think? Is the mantle made out of felsic material or mafic material? Which one is the most dense? Here, mafic rock is more dense, felsic rock is less dense. So since this is mafic stuff, what do we need to do to it? Make it light or dark? Mafic is dark, felsic is light. So this is the same stuff as what's in the ocean crust. Ocean crust and the mantle are made of the same materials. So now, the next thing to draw would be the currents down in the mantle. So I think we've been over this, except for the new people, we've been over this enough, and even probably new people, if you catch on quickly, to be able to draw the currents that are causing all this. So think about it before I reveal it. Right here, is this going to be a rising or a sinking current? Anybody? All right, nobody's answering. I'm going to do this because this is easy. I'm going to do that because that's easy. And I know this because the plate moves that way. And the current in the mantle's like a river, and this is like a raft on the river, and the mantle's pushing it that way. So if the plate goes to the left, the mantle goes to the left. So back to this. What kind of a current's going to cause? Yeah. So here we go. This goes up, and then it goes like this, and then it goes like this. And I bet you can imagine which way it goes here to complete the pattern. Left or right? Left. So these are the mantle currents. And this place right here is, I think, one of these questions down here. Number 8 says, the mantle below this area is relatively cool. Number 10 says, the mantle below this area is relatively hot. Which one of those is true? Hot. So if we're checking these boxes off, number 10 would definitely work, or you could darken the box maybe. And we know it's hot because, blurt out, how do you know it's hot? It's rising. Rising currents are hot. All right. Now, where these two things meet, this is kind of a funny one, and I don't really care about this too much, but I'm just going to draw these a little farther over, and then I'll use my fingers since on the video you can't really see the rest of me. So right here where they meet, would you expect these two plates to just meet like this, straight? Would you expect them to kind of curve up a little bit like that? Or would you expect them to curve down a little bit like this? Which one? Are they gonna go up, be straight, or go down? What makes the most sense based on the picture? Naya? Why would you say they would go down a little bit? They go up. Why do you think they go up? Yeah, so there are two reasons that they'll go up a little bit. And the way I usually describe this is it's kind of like two canoes facing off with one another. So one of the reasons they go up is because some of this stuff that's rising, since they're getting pushed apart, there's a crack here. And this stuff comes up to the surface, and it actually comes out right there. And what happens when you heat something up? When you heat something up, does it shrink or does it expand? Naya? Expand. So this whole area right here is hot. So that's going to make all the ground expand upward a little bit. Plus there's a current pushing upward. So that makes this rise up some. So I should make it rise up a little bit more, in fact. So this, when I wrote Mid-Atlantic Ridge before, the ridge is this. There's the ridge right along this edge. And the other thing, since it's ocean crust, let's do some water. And there's something else I want to add, but I'm not sure if I should add it yet. I think I will. And I want to, no, I don't want to show it to you. I'm going to draw this. You don't need to draw it. I'm going to draw a continent over here. So here's a continent. This is the edge of the ocean. This continent, should I make it dark or should I make it light? Oh, come on. Continental crust, I'll make it light. So the continent's light. That's why it sits up so high. The ocean is dense. That's why it's down a little bit lower. And rain starts to fall on the continent. Here's a rain cloud. Over thousands and thousands of years, the rain falls on this continent and then washes into the ocean. And what gets carried with it? After we've talked about this. After a big storm in Vermont, what does Lake Champlain look like? It looks cloudy, and the cloudiness is sediment. And where does the sediment come from? It washes off the land. It washes from farms and from streets and everything, and it goes into the ocean. So what's going to happen is sediment, little bits of the continent are going to wash in here, and they're going to settle on top of the ocean bottom. So there's going to be this layer of white stuff on the ocean bottom. But I'm not just going to draw a layer of white on the ocean bottom because it's more complicated than that. Look at the picture, and I'll give you two choices. Either right here at position A, don't draw A, I'm just doing that, or B over here. So either close to the ridge or far from the ridge. Where's the new ocean crust being born? Somewhere in here, you've got new rocks being born. There's lava that's hardening and turning into rock. Naya, where's it being born? At A. So what happens is this magma comes up, or this molten rock from the mantle. It gets to the surface, it touches the water, it cools off, it gets hard, it sticks to this edge. But it doesn't really build up too tall because it gets split apart. So you don't get a really tall volcano because it keeps splitting. And eventually the stuff that's right here is going to get pushed this way. So whatever's right here at B, this is really old, and it used to be over here. It's like a conveyor belt going like this. And same thing over here. This is really old rock. It used to be right here. This is where it was born, and it got pushed this way. So if you go through your house, where would there be the most dust? on things that are new that just got set down yesterday, or things that are old that got set down a year ago. Old things. So here's how you draw your sediment. Start it thin at the mid-ocean ridge or the mid-Atlantic ridge, and then make it thicker and thicker and thicker. So starts thin, and I know your picture may not be super nice, but if it's not super nice, you can look back at the picture I did, and you can see that. So this stuff, label this light stuff. I'm going to call it felsic sediment. And I'm going to label this is new rock. And over here, I'm going to label this old rock. And I don't think I'll really go into explaining on here why the sediment's thicker over the old rock, but it's because it's had more time for dust to settle on it. And this new rock doesn't have much dust on it. Sediment's like dust. Think there's another thing to add here. Do you think you could ever have an earthquake in this area? An earthquake is when the earth basically moves with a jerk. Do you think that could happen, that suddenly these plates could go? Well, sometimes they move really smoothly for long periods of time, but they actually could. And so in all these diagrams, I think I'm going to be asking you, could you have an earthquake here? And the answer is yes. You could have an earthquake even out in the middle of a plate. It doesn't happen much. But as this magma burps up to the top and pushes this apart, every once in a while it's going to do it in a kind of jerky way. So let's see. Let's do the checklist. Or maybe let's do this. Let's flip. Yes. So let's flip over and look at some of these. It's kind of a preview of what we're going to be doing. What we just did is like, yeah. I feel like the one that I'm looking for is missing, but it may be because I've ripped my handout open. Okay. So it's right down below the map. So this is kind of what we were just drawing. We've got a ridge, we've got new ocean crust, we've got thin sediment, we have thick sediment, older ocean crust. So the thing is, if you have magma come out here and it starts to pile up and form a volcano, that whole volcano is going to get split apart. And then you have the crack open up again, and then you get more magma, and then it splits apart. So it's like anytime you do this, then this whole thing gets broken apart, and it's going to look like this. Then you have some new stuff start to form right here, but then that gets broken apart and it moves apart. So you end up with a lot of like old ridges out here, but nothing. It's not like this just gets higher and higher and higher because it keeps splitting. So the places where we do get really tall volcanoes are a place like this, where we'll get to this at some point, where the crust comes down. And why would the crust melt when it gets down here? It's hotter. So it comes down here and gets really hot. And there's water mixed in with this. And the water starts to form bubbles, and that rises and melts its way through the crust. And then it all starts to pile up right here. So new crust comes in, and it's constantly just melting more and more and more. And this stuff rises up and grows. So this kind of volcano never gets broken apart. It just sits here by the coastline. But the one that we just drew, they don't get really tall, except the only place, in fact, let me show you this. The only place where you get anything going up above the Earth's surface, or above the ocean surface, is Iceland. These are just a bunch of different pictures of things. So right here, this part that I'm going over, that's the mid-ocean ridge looking from above. This is Greenland. This is, I think, maybe the British Isles, and there's Iceland. It's just this one freaky place where the two plates, they're not going apart faster than this stuff is building up. Whoops. Why? So here's another picture of the Mid-Atlantic Ridge. This is right here where the two plates come together. All right. I guess I didn't have very many pictures of the Mid-Atlantic Ridge. Back to there. Let's go through the checkbox. Where it says steep composite cone volcanoes, there aren't going to be any really big steep volcanoes, and you don't even know what composite cone volcanoes are yet. So that's going to be a no. Ocean trench, that's another thing that when we get to it, you'll know what it is, and that's a no here. This is a good one. You should be able to figure this one out with a little bit of help from me. So, can lava come to the surface and erupt? Yes. And look at the source of that lava. Is it the light stuff or the dark stuff? It's the dark stuff. So it's this. It's mafic. And mafic lava, is it the, here's mafic. Is it the runny kind or the gooey kind? It's runny. So when this stuff comes to the surface, this runny lava, is it going to cause relatively violent eruptions or gentle eruptions? Does the runny stuff explode? Does the water explode when you boil it, or does it's the tomato sauce that explodes. So this is going to have gentle explosions. So number 4 would work. So that's one thing we have here. We've got really relatively gentle. If you ask the people in Iceland, are their volcanoes gentle? They would say no. But they're still alive. Whereas if you ask the people at Mount St. Helens if their volcano was gentle, they can't answer because they're dead. It's very explosive. And people miles away from Mount St. Helens were killed by the volcanic blast. So there's a big difference. So shallow earthquakes, you don't know the difference between shallow and deep yet, but this one, shallow earthquakes, you can always have. Shallow earthquakes are earthquakes that happen sort of at the level of the crust. Anytime the crust is moving, anytime lava is burping its way out of the earth, you can have those. Deep earthquakes, again, there aren't any here, but we'll get to one in a little while. Subduction zone, that's when one plate goes under another, so there's none of that. The mantle is relatively cool. I know we've been over this, but is this true? Is this a cool spot that would do this? No, that's hot because it's rising. Tall mountains, but no volcanoes? No, there's volcanoes, and so that's not true. And then there are rounded shield volcanoes. I'll tell you what those are later. So that's all we have for that. It's 12:52. Let's take a 5-minute break. I know I've been talking at you a long time. You've been sitting in your seat. So if anybody needs to go to the bathroom or get some water, this is a good time to go. And